So now we're going to use the theorem to find the Laplace transform of some harder functions. So the first example is we want to find the Laplace transform of t times e to the kt. Okay, so this is not easy to find if we use the definition with integrals. So let's see if there's a different way to do it. So first we let f of t equal to t times e to the kt. The product rule tells you that the derivative is equal to e to the kt plus kt e to the kt. Moreover, notice that f of 0 is equal to 0 because there's a t in the front. So if we apply Laplace transform here on both sides, the left-hand side is equal to, according to the theorem, this is equal to s times the Laplace transform of f of t minus f of 0. Okay, and notice f of 0 is 0 because our function this is equal to 0. So this is equal to s times the Laplace transform of f of t is t times e to the kt. So we get s times the Laplace transform of t times e to the kt equal to the right-hand side, which is equal to the Laplace transform of e to the kt plus k times the Laplace transform of t times e to the kt. These are the same terms, so we can move terms around. We get s minus k times the Laplace transform of t e to the kt equals to the Laplace transform of e to the kt. But we know what this is. According to the table, this is equal to 1 over s minus k. And that's it. So divided by s minus k on both sides, we get the Laplace transform of the function we are looking for is equal to 1 over s minus k squared, with no integrals at all. All right, so let's do a different example. Let me erase most of this part. We're still going to need the theorem, so I'm going to erase this part. Okay, so suppose we want to find the Laplace transform of t times sine of kt. So it's the same way. We let f of t equals to t times sine kt. Notice that f of 0 is still equal to 0, and f prime can be found using the product rule. So it's sine kt plus kt cosine kt. And notice that f prime of 0 is still 0. Now they take the derivative again. So f double prime is equal to k cosine kt plus k cosine kt minus k squared t sine kt. And so we get the second derivative is equal to 2k cosine kt minus k squared t sine kt. And let's take the Laplace transform on both sides. Let's use blue. Laplace transform on both sides. The left-hand side, according to the theorem, is equal to s squared times the Laplace transform of f of t minus s times f of 0 minus f prime of 0. But we know these are both 0, so we don't have to worry about them. So this is equal to s squared times the Laplace transform of f of t, which is t times sine of kt. Okay, so let's move to the right. That means s squared times the Laplace transform of t sine kt is equal to 2k times the Laplace transform of cosine kt minus k squared times the Laplace transform of t sine kt. And notice that these are the same term, so we can move them together. So we get s squared plus k times the Laplace transform of t sine kt is equal to 2k times the Laplace transform of cosine kt. If you look at the table, this is equal to s over s squared plus k squared. So it's equal to 2k times that function. So now we have the Laplace transform of the function we're looking for, divided by s squared plus k squared. There's a square here, I forgot. Divided by s squared plus k squared, we get the Laplace transform of t sine kt is equal to 2ks divided by s squared plus k squared, 2 copies. So this is a special way to find the Laplace transform of some Potter functions.